So let's start. I would like to welcome you all to the Mathematical Institute for another public lecture. My name is Alain Gorielli and I'm in charge of this series of lectures for the department. So before we start, I have to remind you about the Brexit sign. There are 1, 2, 3, 4, 5. It seems the government cannot quite decide which one is the best to use to leave the building. We do not plan to have any trouble, but in case of emergency, do not wait for the government, just go for the nearest exit. Okay, very good. So if you might have seen now, we have nice sign now, and you might have seen that little extra symbol, which looks like a matrix with the sign X there, XTX Markets. It's actually not a mathematical sign, but it's a financial company, XTX Markets, which is based in London. It has office in Singapore and New York. And it's generously supporting not only this lecture, but the entire series. So we're very grateful for the support. So a lot of you have come for a major event. This is it tonight, of course, but we have another major event bringing a lot of eminent mathematicians from around the world in this building this week. It is the 70th anniversary of birthday of Professor John Ball, that you will see in a minute, so we wish him very well. According to Wikipedia, his actual birthday is on Saturday, I found out. Just wait for a couple of days. So a part of this celebration, we have, of course, many very high quality, very advanced talks from different mathematicians, but we thought also we would bring something to the public. And we thought that for this special event, we'll try something different. And that you can see, we have a very cozy setting here. And the reason is that tonight's speaker is Michael Atiyah. And Michael Atiyah, as such an influence, is so eminent among mathematics, in modern mathematics, that it would be completely overwhelming for me to even try to introduce him properly. So instead of that, Michael Atiyah, Professor Atiyah, will give a short lecture about certain ideas that he has about numbers. And after that, he will sit and we'll have a nice conversation, a dialogue with John Ball regarding his life, mathematics, their contribution, and so on. So we hope that you will enjoy, and I think it will be a very exciting and very enlightening event. So without further ado, please help me welcome Professor Atiyah for this special event.
Well, thank you very much for the introduction, and I'm delighted to see such a large audience in support of mathematics in this famous building. I spent many, many years in Oxford, and although I've not long since retired, it's nice to come back, see so many friends. Now, this lecture, there's the title of the lecture. It's the Titchmarsh Lecture, University of Oxford, and I'm from the University of Edinburgh and also from Trinity College, Cambridge, so that you know who I am. Now, I think if I press a button, suddenly something happens. Let's see. No, it doesn't. Technology support needed. What's happened?
You can always press the...
But you told me if I press this, it'll be okay.
Yeah, let's see.
See, it doesn't work.
So you can press this mouse button, that should work.
Let's try this one.
Yeah.
No, this doesn't work either.
This one.
You see, technology is not perfect.
Oh, okay. Do you want to just, if you push on any keys here.
Well, let's go back to give me the first one.
Yes, this one.
No, I want to go next.
This one.
Okay. Sorry, no, I keep it. Small hiccup. It makes it more exciting. Okay, so the title of my talk was Numbers are serious, but they're also fun. If you're a mathematician, you enjoy doing mathematics, whether you're young or old, and so it's fun. But sometimes you do also, if you play fun games, you can also get some serious outcomes. And so I want to show you how that works. And so let's start very far back in history of time with the greatest mathematician of all time. That was Archimedes. Without question, one of the great geniuses of history. You all heard about Archimedes. He's famous for lots of things, one of which is he jumped out of his bath and ran down the street shouting Eureka. In those days, people were more tolerant. And you may not know this, but he also, by the way, if you don't know what Archimedes looked like, you can find out. All you've got to do is to win a Fields Medal, and there's his picture. So I have a Fields Medal, which I've done in the University of Cambridge, and there is the picture of Archimedes, guaranteed by Wikipedia. Now, Archimedes did many, many things. But one thing in particular, he invented the number of pi. Now, I think you all know what pi is, most of you. I noticed downstairs there's a cafe called the Pi Cafe. So pi is so famous it has a cafe. Now, pi is a number that tells you something about the circumference of a circle, and it's a very important number, and there it is, written down a few decimal places, 3.14, and so on. So pi is a very important number in history of mathematics. It was invented by Archimedes. Now, second famous mathematician, a lot later, about 2,000 years later, was Leonard Euler. There's a picture of Euler. He was a remarkable man. He published so much that they still haven't finished editing his works 100 years after he died. And later on, last part of his life, he was going blind, but that didn't stop him. He carried on right to the very end. He produced a vast amount of work, and almost everything that mathematicians now use goes back to Euler. Now, for example, Euler invented numbers just like Pythagoras invented numbers. Pythagoras invented Archimedes, this with the tongue. Archimedes invented pi. Euler invented a number called E. E, well, what is E? Well, it's written down there for you. It's 2.718 and so on. What is it? Well, the easiest way to describe it, if you don't know what E is you go to a friendly bank which offers you, let's say, 100% interest. It's a very friendly bank. So you give it £1 at the beginning of the year. At the end of the year, it gives you interest 1, you end up with £2. Good profit. But suppose you decide to take your money in installments, take the first bit after 6 months, and the bank is also friendly enough to give you the same rate if you do compound interest. Then when you come to the second 6 months, you get not only interest on the whole money, interest on the interest. You add that in, obviously it's a bit more than 2. But suppose you took your interest every quarter, and every quarter of quarter. So in the limit, how much would you get? The interest amount you'd get would be E. So E is the amount you'd get from a very friendly bank. Now, of course, fortunately, the formula is such that you can work it out, whatever the interest rate is, by a small change, E still gives you the answer. It's a very useful number, and you might say, well, I'm not interested in money, but suppose you count something else. Suppose you want to count populations. You breed rabbits. Okay, you start off with 2 rabbits, shortly you get 4 rabbits, and 4 rabbits. And that is called exponential growth. And world population sometimes suffers from exponential growth. And that's also come by E. So E is a very important number. E nowadays stands for exponential. Things which go by multiplication, and the same formula. So Euler invented E, very important number. Now, one of the things that happened before Euler was people discovered things called complex numbers, things that don't exist, imaginary numbers. If you square a number, whether you start with a positive number or a negative number, the answer is positive. So this -1 cannot be the square of any number. But mathematicians aren't put off by things that don't exist. Still, it's an imaginary number. You can imagine I, and we call it I because I is imaginary. So I became an imaginary number. There was always some doubt. There was some skepticism. Are you allowed to use imaginary numbers? Well, yes and no. But eventually they found it was so useful that they allowed it. And Euler combined these two together. He took the I, and he said, suppose you take E and you raise it to a power, and you raise it to a power using Archimedes, you put in pi, you write 2 pi I, and then with this marvelous collection, you get the value 1. And this formula, e to the 2 pi I equals 1, is regarded as the most beautiful formula in mathematics. Any mathematician who knows, you ask them, almost without exception, this is the most beautiful formula in mathematics. It's fantastic. It combines important numbers, pi, e, I, and you get 1. It is staggeringly beautiful. And it is so famous, so beautiful, that it's this, if you only want to invent one thing in your life, you could do that and you're famous for life. But Euler invented many things, but this was one. I like to explain it to people who aren't mathematicians like this. If you ask in literature, and mathematicians, by the way, are not illiterate. We can read. And if you know your Hamlet, Shakespeare, there is a famous phrase, to be or not to be. It's very beautifully short. Use only 2-syllable letters, to be. It's extremely short. And yet, if you think about it, it's a very deep statement. To be or not to be, basically, are you going to kill yourself? Well, so what could be more important than that? And so I think Hamlet, Shakespeare, to be or not to be, is the literary equivalent of Euler's formula, or the other way around. Euler's formula is the mathematical equivalent of to be or not to be. They are 2 perfect gems, remarkably short, succinct, and yet deep. That is what you aim to achieve in mathematics or in literature. I hope you're convinced. That was my first slide. I don't have many slides. I don't believe hundreds of slides one after the other. Fortunately, because it doesn't always work. Now, I'm going to spend the next bit talking about my wife. Hope you don't mind, it's personal. My wife, Lily, sadly died a few months ago, was a mathematician. And women mathematicians were rather rare in her time. And she had a successful life as a mathematician, in many ways. And she, the picture shows here that together we donated a collection of photographs of mathematicians to the University of Edinburgh, where we are now, and we opened it together. So that was her last public appearance in 2014. And before that, she taught in many places. And she taught, in particular, at St. Hugh's College, Oxford, which you probably know down the road. And so we spent many years at Oxford, and that's what part of her time was spent there. And then if I press another button, I think it'll work this time. Yes, she also taught at Headington School, which is not very far up the road, a girls' school. And I'm very pleased that Colin Petford, sitting in the front row here, who was a fellow teacher of Lily's all that time ago, was here for the occasion. She taught mathematics in Headington School for quite a long time. And since I've been here in Oxford this time, I've been told by 4 different people that their daughter was taught mathematics by my wife, and that altered their careers. So if you teach children, any age, inspire them, you can alter their lives. My wife had that ability. She was also very active in the Mathematical Association, which involves the whole involvement of teachers teaching mathematics in schools of all kinds. She was very active in the Mathematical Association here in Oxford. So I think it's, since I'm back in Oxford, and we spent 30 years in Oxford together, and she passed away a short while ago, I think I'd like to dedicate this lecture to my wife. So, by the way, I should mention, for those of you who've been attending a conference to John Ball, and who will appear shortly, it's like a miraculous appearance, that my wife did a PhD in mathematics. She worked with Mary Cartwright, a very famous woman mathematician, and in fact her work, which was really quite difficult stuff, which I didn't really understand when she did it, is actually turned out to be, on reflection, quite closely connected with some of the things we've been hearing about in John Ball's lecture. So she did work of some mathematical importance with her PhD, but in those days it was unheard of. When I got my PhD, went off to America, in those days she had to give up her job and follow me. Nowadays you wouldn't do that. You'd send your husband away and say, well, see you when you come back. But in those days it was customary to resign your job. She had a full university job teaching mathematics a year before me, and when we got married, she had to leave and go away. It's sad, but that's how it happened. Right, so that was my dedication to my wife. I hope you don't mind my little digression. Now back to the main theme of my lecture. So we looked at the past, Archimedes and Euler. Great figures. They did marvelous things. Well, how about the future? Well, somebody in this audience here, future Archimedes? Any Greeks here? Future Euler? Actually, we all come from all parts of the world. It doesn't matter where you come from. Mathematics is absolutely universal. So anywhere in the world you come, you can try. So there's a challenge problem. I offer you a challenge. Well, play around with numbers like Archimedes and Euler and invent a new number. Look, Archimedes invented pi, Euler invented e, and e to the 2 pi I. Why not try your hand at inventing a new number, and you will become as famous as Archimedes or Euler. You know, only one kind of immortality, that is the immortality of ideas. Your body passes away, but any fundamental ideas you create live on. That is real immortality. So do you want to be immortal? Don't buy medicine to live longer, just work hard, have ideas. Now, I don't want, as I point out here, you don't need to jump out of the bath to become famous. That's extra, it's a bonus. But if you look around, you see, when Archimedes found pi, it was been around. Everybody knew that somehow if you have a circle and you had to travel around the circle, its length was approximately a bit more than 3 times. You know, people who know practice, everybody could, roughly speaking, see that. After all, we know that the shortest distance between 2 points is a straight line. If you go out in a curve, it's going to take longer. So how much longer? Well, people knew there was something. So Archimedes made that precise. He said, well, I know what it is, and you did it this way, and here's how you calculate it, and this is the number. So he was taking some material and actually formalizing it, telling you what it was. So the question is, if you want to do something similar to Archimedes now, what should you do? Well, you should look around and see what people are doing. What are the common equivalents of the people who are doing primitive agriculture now? Well, of course, they're more sophisticated, and they might be called physicists. And if you look around amongst your physics friends, you'll find that they have a number. And the number has a name. It's called the fine structure constant. Now, you don't need to know anything about what the fine structure constant is, but clearly something that has a name like fine structure implies that it's something rather fine. And so it is a marvelous thing. Physicists love it. And actually, whether you talk about the number, which is called alpha, well, you have to think of a letter of the alphabet, first comes first served. Well, alpha. Sometimes people write 1 over alpha. Well, it doesn't much matter whether you have a number or it's inverse. Each gives the other, so I prefer to write 1 over alpha. And this number is known quite well. Here it is. It's 137.035. Well, you can read it to yourself. That number is known. But what is it? Now, see, people now know a lot more than they did in the early days. They're quite more advanced. They have pocket calculators. They don't need to think. They press a button, hopefully. So they know this. But what is it? Well, let me give you a quotation from a physicist, very famous physicist. I'll show you who he was. He was called Richard Feynman. And there's a picture of Richard Feynman. He got a smile on his face. He was always making jokes, but he was one of the great physicists of the 20th century, unfortunately now dead. And Richard Feynman said the following thing. So I'll read it to you because it's very powerful. But let's say, first of all, if I swear, it's not me, it's Richard Feynman swearing. So I hope I'm solved. Now he says, where does this alpha come from, this number? Is it related to pi or perhaps e? No, he thinks back to Archimedes, Euler. This new number, well, where does it come from? It's a number that emerges from physics in some marvelous way, but nobody knows quite much about it. He says, nobody knows. It is one of the great damned mysteries of physics. There you see. It's Feynman swearing, not me. And a magic number, now everybody likes magic, wave in the air, abracadabra, a magic number that comes to you with no understanding by man. Where does it come from? You might say that the hand of God wrote the number. If you're theological, well, I don't know what that means, but and we don't know how he, notice the capital letters, he pushed his pencil. So this is what Feynman said. It's a challenge. Can you answer his question? What is alpha? You know something about it, but you don't know where it comes from. Where is it born? Who is it? Where does it belong? Is it related to pi? Is it related to E? Well. I think the answer is yes. But I better not spoil your fun. You go away. If anybody gets an answer, come back and give it to me. If not, I might leak the secret privately. So that is the great problem. It's a good example of a challenge. You can look at numbers, play with numbers, but play with interesting numbers. Play with numbers that might be important. This number is not an arbitrary number. It's a number that plays a very fundamental role in all of physics. Everywhere physicists look, this pops up. Because think about pi. Pi doesn't just occur in the circumference of a circle. All physicists know that pi occurs almost everywhere. If you look at Gaussian distributions, you find pi. If you look at this, you can everywhere you look in mathematics, pi props up. Why? Well, God only knows. And this number here, apparently it's the same. It's a number that pops up everywhere you look. You do an experiment with this and that, it's there. You do another experiment, something else, it's there. Same number, and also always there. How does that happen? It's magic. And magic is really the great beauty of mathematics. It is fun, enjoyable, yet deeply serious. It tells us things about the world we didn't understand. And even when we've done it, you stand back and admire the miracle. So it is really mind-bogglingly spectacular. And so I think if we solve this problem, we really done a lot to increase our understanding of the universe and increase our understanding. So it is a challenge. And if you have, any of you want a challenge, there it is. But it's not an easy challenge. I should tell you that this has been around for, let's say, at least 50 years or more. So, and many people have tried to solve that problem and got nowhere. So, but that's always true of all the great problems of the past. They've been there around sometimes hundreds of years. Well, think of Andrew Wiles solving Fermat's last theorem in this building. The building comes after. And so problems may have been around for 50 years, 100 years. And of course, nowadays, things move much faster. 50 days now with Google and all that is equivalent to several hundred days. So, things are much quicker. So you'd expect after 50, 60 years, this problem would have been solved. But it hasn't. There's a real challenge. Can you keep up the pressure of advancing mathematics by not just doing little calculations? That's a dull sort of game. But solving fundamental questions which have a long history and a great importance and a great beauty. And of course, when you solve this problem, you don't only want to understand this new number, alpha, but you want to ask, is there some relationship, some analog of Euler's formula with 2 pi r equals 1? Does this have something to do with that? Because that was the ultimate beautiful formula, the one that I said equivalent to be or not to be. Well, Shakespeare was a great writer, but there are other great writers. Is there something else which goes beyond the Shakespearean quotation? Well, so you see, life, mathematics, literature don't stop. There's always room for new things. And so with an audience full of some young people, some not so young, I offer you this challenge. Can we push the boundaries of what we know a little further? But if you don't do that, we're just copying our ancestors. And by the way, we had a lot of discussions at some of our meetings about modern computers. Will the computer replace the human mind? Will artificial intelligence make us all redundant, out of work? People think there's a lot of serious talk these days about replacing the human brain almost entirely by artificial intelligence. Well, fortunately, I'm a believer in that you cannot do that. I think artificial intelligence of any kind, however sophisticated, basically has limitations. And the human mind does not have those limitations. And the human mind has evolved over several billion years through evolution, and no amount of clever manipulation by computer scientists is going to catch up. So that cheers you up. You're not going to be done out of a job. Stay with mathematics and think, not just, don't do routine calculations. The computer will wipe that off the board very fast. That's dull. Think deeply, think imaginatively, have brilliant ideas. Think of things that nobody would think of, even a computer. Then you're ahead. So there's the left message for you. Let's encourage you for the future. Don't be depressed. Just remain enjoying doing mathematics, enjoying the fun of it, and realizing that at the same time you can do something important. Well, I think I've used up my time, and I now will move to a comfortable chair. Oh, yes.
Maybe you keep
No.
it for the...
Sorry, I noticed there was another slide left. So sometimes technology is useful. Yes, I should have said, this lecture is of course called the Titchmarsh Lecture. So I should say something about Titchmarsh. Well, actually, I shouldn't say much about Titchmarsh because Titchmarsh himself was a man of very few words. He's very similar to the famous physicist Paul Dirac, who was also a man of very few words, and I'll tell you a few stories about that. So they spoke very little. And so when I came to Oxford, I had to go to the old building, not this grand building here, and I had to get the keys to my office. That was in 1961, sometime back in the Middle Ages. And I had to go and see Professor Titchmarsh because he was the senior professor. So I went into his office, I sat down, he gave me the key. I sat and waited. 5 minutes, nothing happened. I got up and walked out. He wasn't a man to waste words. And actually, a few years later, he died, and I took over his office, but that's another story. And now let me tell you about Dirac, since I'm talking about people with few words. Now, Paul Dirac was the most brilliant physicist of the 20th century after Einstein. In the hierarchy of physicists, Einstein is way up there, Dirac is just after him, and the others are sort of a bit low. That's modern physics. I mean, if you go back, we include Newton and so on. And Dirac was a remarkable man. Now, he had an interesting background. His name was Paul Adrien Maurice Dirac, so obviously French origin. And his father, who'd come to Britain from, I've forgotten which French-speaking country he came from, now Switzerland or Belgium. Anyway, he was very keen that his son should learn French. He was so keen that he insisted that at all meal times you didn't get any food unless you spoke French. Well, if you have any experience with children, you know that this is not very productive. So the outcome of this was that as soon as Dirac left home, A, he stopped speaking to his father, B, he stopped speaking French, and C, he almost stopped speaking. So he became a man of very few words, and that's true. He really cut his father off completely, and he never spoke French. I mean, trying to indoctrinate your children by force is counterproductive. Now, I'll tell you one story and then I will stop. To give you an example, Dirac, everybody knew that he was a man of few words. On one occasion, he was a fellow of St. John's College, this is Cambridge now, and he went into lunch one day, or dinner, and sat down, and a young lady sat down beside him. She said to him, "Professor Dirac, I've taken a bet that you will say at least 3 words to me." He turned to her and he said, "You lose." So you see, he was a man of few words. Okay. So I will follow his example now, sit down. Okay. Now I take the comfortable chair. Sorry, this is the hot chair. Right, John. Nice to meet you, sir. A young 70-year-old.
Yes. So thank you so much for this inspiring lecture. So maybe I could ask you a question
Yes.
on the lecture
Yes,
first.
of course.
So you think there should be a formula for the fine structure constant, or related to Euler's formula?
Yes. I'm a man of few words. Well, it depends what you mean by formula. See, mathematicians always have to question, what do you mean by? And formula, there's actually no formula. Well, even pi, there isn't really a formula for pi. There's a procedure for calculating pi by going through some complicated limiting process. And I claim that this number has all the properties that you think of as pi, but it's a bit more difficult. Yes. So it is a number with a good ancestry.
Of course, it's a dimensionless number from physics. So you think there are other dimensionless numbers from physics?
Yes, I think
that
that
be thought of the same way. Or?
You see, in physics, usually you measure things in terms of units, velocity, speed, distance over ratio, mass. So most things in physics depend on the units you use, and you change your units, metric to meters to centimeters, you have to rescale things. But sometimes when you take a ratio of two things which have the same dimensions, then they cancel out and they have no dimension left. So they are not pure numbers. And that's pi as an example. If you have a circle, radius is 2 pi r. If you take another r, you cancel the r, and you get pi. So pi comes by cancelling all the dimensions. And you can do that with other quantities, and this fine structure constant is an example. It's a dimensionless number, therefore a pure number. If it's a pure number, it comes from mathematics. Ha! That's it.
So there's a lot of young people here from local schools. I think they might be interested to know how you first got interested in mathematics. Was it an inspiring teacher, your parents, a book you read, a problem you heard about?
Well, very often people say, yes, somebody inspired me. And, teachers can be very inspiring. My wife was a teacher. She was very inspiring. So I think I was fortunate in a way. I didn't have to be inspired by a teacher. I just naturally inspired myself. I mean, and I had perfectly respectable teachers. Later on, I got some quite good. I had a good, very inspiring teacher rather late in life. Late in life meaning when I was 16. I mean, by that time, your education is nearly finished. So when I was 16, I was sent to a school called Manchester Grammar School because they were supposed to have a very good mathematics preparation to go to university. There was a teacher there who was really inspiring, very old school style person. He'd been to Oxford, but he thought his best student should go to Cambridge, so I was trained to go to Cambridge. And he was very inspiring. He made us work very hard. I probably worked harder in that year than any time in my life, either before or since. So he was inspiring, but I already decided to be a mathematician before that. But at that stage, he gave me excellent inspiration, yes. Mm-hmm. So any time in your life you may be inspired, maybe initially, or maybe later on. And inspiration is very helpful. That inspiration stayed with me. I still think about him. Mm-hmm. Yes, so teachers can have a big effect on your life. And good teachers, they can change your life in a minute. You go and hear a good teacher or good lecture, and you come away, your life has changed.
And your wife, Lily, do you know what inspired her to do mathematics?
Well, my wife had a very complicated story. She came from a very poor background. Her father worked in the dockyards. Nobody in her family went to any respectable school. So she found she was good at mathematics, and that was her way out of poverty. And nothing more inspires you more than to rise above your roots. So she pulled herself up from nowhere, ended up by being the best woman mathematician in her school, got all the prizes at the university, and doing very well until she met me. That was it. That was her fate. But no, she pulled herself up entirely by her own exertions, her own ability, and she had the brains, and she was, by the way, no good at English. She failed all her English. Mind you, this was in Scotland. So, and But she always had a good mathematical brain, and she used it. So it does help if you have a good mathematical brain if you want to do mathematics. But if you have a good mathematical brain, you enjoy mathematics, and that sort of feeds back and makes you better.
So you're one of the world's most famous mathematicians, and you must have had many great moments, great mathematical moments. But is there one moment that mathematical discovery or moment when you discovered something that sort of stands out among all the others?
Well, yes and no. All good answers come like that. I worked on something which eventually became called index theory. It doesn't matter what it is, but it's a theorem, but it has so many ramifications, it took me 20 years to develop. So it became a theory. And so that was undoubtedly my best work. But it covered, in fact, 20 years understatement. I'm still working on it now. So it takes over your life. And so in that sense, that's the best thing I've ever done. But it's so all-embracing, it includes lots of sub-things. So that's, yes, I think, and if you've done something like that, you tend to know it. You tend to realize that you found a gold mine. And you find a gold mine, you go on digging. Don't go on digging when the gold's run out, but as long as it's there, you keep digging. So, yes. So sorry, I rambled a bit.
No, but it happened at a precise moment, in an afternoon or something, when you suddenly saw what...
Well, there have been occasions like that. There's, of course, famous bridge story in Dublin. Hamilton, the great Irish mathematician, who had flashes of inspiration as he crossed the bridge. And he wrote it down there and then, and now when you cross that bridge, you'll see a plaque saying, "Here, Walter Hamilton discovered quaternions." And that's very... There are many stories in mathematics which are apocryphal. Archimedes jumping out of his bath, well, there's no photographic evidence. Newton and the apple tree, well, there is an apple tree, but it's not quite clear that Newton was sitting under it. So, these are stories which are sort of, they're really myths. But a good myth carries a lot of importance, even if it's not actually true. And so a lot of things are myths. But the case of Dublin and Hamilton is fact. In my case, I'm trying to think of anything. There have been a few occasions in my life. I remember reading that Henri Poincaré, the great French mathematician, used to claim that he got good ideas getting on and off a bus. Well, I tried getting on and off buses. It didn't work. But I remember very clearly once when going for a long walk with, I think, my friend, his book. End of the walk, we'd solved the problem. And during that walk, it was a flash of inspiration, yes. So and I remember that clearly now. It was one particular day, something I've been working on for quite a long time, and we went for the walk, and at the end of the walk, we said, that's it. And there'd been one or two other occasions when a bit like that. Doesn't involve a bus, it could happen anywhere. It could be your bath, it could be this. And so you get these flashes of inspiration, they don't know where they come from, and they crack a problem for you. At least crack a sort of fundamental difficulty, something that's been holding you up. And so, yes, I've had that. A few times, not very often. Actually, I remember, like the story, Einstein was asked once, how did his good ideas come to him? He said, I think I had one good idea once. Modesty,
Now, all mathematicians get stuck when they're trying to solve problems. I feel I'm stuck almost all the time.
Yes.
So what do you do when you're stuck on a problem?
Very good question. Well, answer is experience helps. The first time you're stuck on a problem, it can be devastating, and people don't know what to do. But with a bit of experience, several things you do. One is you leave the problem alone for a while. You forget about it. You do something else. So you should have a stock of things you're going to work on. When this problem is stuck, you work on that problem and that problem. And then maybe you come back to the first one later on. You have half a dozen problems and you're stuck on each. But you shuffle it round, you find you can make progress. That's one solution. Another solution is you're stuck on a problem and you talk to your friends. Talk to other people. Perhaps they have a different point of view. See, if you hit a wall, brick wall, you can bang your head against the brick wall until your head breaks, the wall doesn't break. That's not a good way of making progress. But it may be that that wall actually is finite, and you go around the wall, and if you've got a friend standing over there, you say, look, why are you banging your head against the wall? And that happens very often. You don't realize that the obstacle you're hitting is not essential, there's a way around it. And another point of view, literally, perspective, can tell you how to do that. And that happens with me. I'm a gregarious mathematician. Sorry, the word gregarious is rather comes from talkative, which means I like to talk to people, and I don't like to sit by myself too long. You've got to balance it in life. You've got to alternate sitting quietly and thinking, and then going away and talking. That's a very good formula for life. Sitting by yourself quietly for a long time, that leads to introversion. Introversion is not healthy. It's also boring. Oscillate between thinking hard by yourself, going out with friends, having a good drink, enjoying life, and mixing those two together. And your friends may say, well, I got an idea about your problem, so you can combine life with problem. That's the way I've tended to work. I tend to be gregarious, talkative, interactive with other friends, and I get that way, I learn new things. The friends teach you something, you learn something. I don't mean you learn technically, you just pick up points of view.
But are the brick walls you've faced for decades, problems that you wanted to solve but somehow couldn't?
Yes, I mean, you could say that all my life I've been trying to solve some really hard problem, and maybe today I've solved it, because you don't know until you've got round the wall whether there was a wall there. So it's a very tricky situation. No, I mean, all your life you're trying to do things, and some big things, you feel that they're lying behind it, and you don't quite know what they are, and maybe at the end of your life you find out, or maybe you don't find out. So we're always searching for the ultimate big breakthrough, whatever that big breakthrough is. And I'm 90 nearly, and I'm still searching. I'm not giving up.
So in your long career, you must have met many famous mathematicians. Does any one of them stand out particularly?
I think I met nearly all the famous mathematicians in the world. Well, almost. I met only all the Fields medalists. That's a good starting point. And so if you live long enough, you tend to meet more people. That's always truism. So I think I've met everybody. And what is remarkable is the variety. Mathematicians come in all shapes and sizes. And people outside mathematics think we're all the same. A mathematician is a peculiar character who likes mathematics. Actually, that's not true at all. We like mathematics, but we're a very varied lot. There are tall people and short people and fat people, and of course, much more significantly, those who work on this kind of mathematics, or those who work on that kind of mathematics, those who work this way or those who work that way. We are a very good, broad cross-section of humanity. And so that is, the diversity of people is actually a very healthy sign in mathematics. I didn't know where I started on this, but I got one thing going, I keep going. What was the question?
Well, was there anybody in particular that you remember as standing out in some way?
Well, let me say, I've met many mathematicians who are obviously streets ahead of me in some direction. For example, Hormander was much better than me at analysis. I learned from him. And I've met Jean-Pierre Serre, who's much better than me in number theory. And I met many people who obviously tremendously impressive in sheer ability to solve hard problems. John Milner, for example, was another mathematician. And I made each one of these I met, I said, well, I can't possibly compete with these guys on that score because they're just better than me. They've got a brain that is very good for this. My brain is inferior in some sense, or different. So, yes, I've met a lot of people who There are about 6. Ed Witten, as an example, physicist. He's a genius. So there are people who are really good. But every genius has his weak points. Well, it's more or less by definition. A genius is somebody who's so focused on doing something that he doesn't notice something else. I never knew Ramanujan, but he had his weaknesses too. So that's if there was one genius who knew everything, it'd be very depressing. I think if there was one person like that, it was Archimedes. Fortunately for me, he lived a long time ago, and I got his medal, so I feel I can. But he would have been, if I had been around in Archimedes' time, he would have been a daunting figure. And but nowadays there are great mathematicians of all kinds, and I can list lots of them, and they're all better than me in some particular niche. But they're not all better in all directions. So that's fortunate. Yeah, but it is interesting, the diversity. The same thing is true if you're a musician. You may be much better at doing piano concertos than some other musician, but he's better at the oboe, the violin. And so, there's no single musician who is equally good across the entire range. Or no writer or a poet who's equally good at writing, large tragedies and small comedies. Shakespeare got pretty close. And, so there are people who get close. So those are the real, Archimedes, Newton. So they're all very big figures. And in my time, I've got to know quite a lot of mathematicians who fill these niches. Yes, and it's nice to have them because you learn from them both the skills and limitations of the human mind. So, that's what we do in life. We learn to live with our limitations and take advantage of our assets.
So as well as being a great mathematician, you became president of the Royal Society. That was a very different job to do, talking to governments and so on. So was that a sort of shock to do that? Did mathematics help you in the job?
Well, I'll come clean. I'll tell you exactly. I was approached by the then President of the Royal Society to say, the council decided we'd like to invite you to be the next president. I was horrified. I said, good Lord, I'm a mathematician. I had no idea how to run the Royal Society. You're a real scientist. And so he said, well, think about it. So I went back and thought about it and talked to my wife, should I take on this job? I'm not a scientist, I'm just an ordinary mathematician. And I really was very unsure. And finally, after a lot of hard thinking, I said, perhaps it's my duty to take it. Now, partly I was influenced by the fact that I'd had all my life, fortunately, from very early on, I had jobs which allowed me to do my mathematical research, which involved a lot of teaching my youth, but then later on less and less. And I was a really free man to spend my time doing mathematics. And I thought, and now by this stage I was age 60, and I thought, well, I've done my mathematics. Perhaps now it's time for me to repay to society in some other way. Maybe my days as a creative mathematician finished. So perhaps I should take on the job. I took on the job as kind of sense of public duty. Of course, once you take it on, you've got to learn the job. And I learnt, that running an organization which has its problems. The Royal Society was a very old organization, had very distinguished people, scientists, but they'd always sometimes messed it up. And I came in as a young radical. Well, I was 60, but I was still a young radical in that sense. And I made a lot of changes. I changed the Royal Society in lots of ways. I can tell you privately later on. I'm glad to see that subsequent presidents have carried on the tradition. But an old institution, lives on its past, but it had to change with the times. And I felt the Royal Society wasn't changing fast enough. So I gave it a kick in the pants. That was my contribution.
And after you had done that, did you find it difficult to get back to doing mathematics?
Well, first of all, I didn't do that on its own. I was simultaneously Master of Trinity College, Cambridge. So I had a double whammy, as they say. And so I thought, well, that's fine. I'm fully engaged in public service. So I've done my job as a mathematician. I'm now, going to perform my duties, and then I will go on the scrap heap, and I'll die quietly. Unfortunately, things didn't work out like that. When I finished all this stuff, I said goodbye to all these duties. Well, what was I going to do? I couldn't possibly keep up with all the young guys who'd been doing mathematics in my absence. So where was I going to get a new idea? Well, fortunately, this is where good fortune strikes you. I got a letter from my friend Michael Berry, who's a very good physicist, and one of his collaborators here, Jonathan Robbins, is here. And he said to me, I've come across this following problem in physics. It is mathematical. It should have a solution. And so he gave me this problem, and I thought, Michael Berry, good man. I looked at the problem. I said, well, look, this is a good problem. It sounds interesting. I look at it, and the more I looked at it, I said, well, first of all, is it true? Is it not true? If it's true, it should easy problem to state. Somebody must have done it. It's not true. I looked at it, nobody had done it. There was this beautiful problem sitting around, and nobody had done it. So I was given this free problem. And I since then I retired, this was 20 years ago or so, and so over that next 10 years or more, I worked on that problem, off and on, in different ways. And that's grown and grown, and now that's the centre of my work. And so it came from responding to a question from a colleague who thought I might be interested, and nobody else could contribute. And yes, that was a gift from God, or a gift from Michael Berry. I mean, God works through Alan Evil. So God has seen me down below. He said, poor chap, he needs a problem. And he got Michael Berry to ask me a question. That's how it works. Yes, it's really true. And I went to Michael Berry's various birthday parties and things and told him I'd solved this problem. And it's kept me going over 20 years.
So you think older people can do mathematics as well as younger people?
Absolutely. I think one of my complaints is that, well, I'll tell you a secret. Sorry. I have some sons, and my youngest son, some say, I told him I had some good ideas. He said, Dad, look, we all know that mathematicians have their best ideas before they're 40. If you want to get Fields Medal, you have to be under 40. He said, you're over 80. It's quite impossible that you have a good idea. If you think you've got a good idea, you're deluding yourself. So how do I disprove that? Well, that's what I've been trying to do. Try to persuade my son that at over 80, and I'm now 89, that you can do good stuff. He's slowly coming around to the idea, maybe I'm right, but not sure yet. So trying to persuade people that you can do good work when you're old is extremely hard. They think you're deluding yourself. And actually, it's not just me alone. If you look back in history, you'll find that all of great mathematicians or physicists in the later years, Einstein, for example. Einstein was without doubt the greatest physicist of the 20th century. He was famous. But halfway through his life and done all his fundamental work, people were doing new things. And he didn't believe in them. He stuck his own roots. And people said, Einstein's past it now. He can't keep up with the times. He's passé, he's an old man. He's not keeping up. And so he was brushed aside, Einstein. And I think I know a bit about it. I've looked into it. I think Einstein was right, everyone was wrong. But they didn't believe him because he's an old man. Same is true of Dirac. When he was young, he had brilliant ideas. Everybody said, great man, Nobel Prize, fine. He got older, he had crazy ideas. They said, oh, he's gone crazy. Old man. And I think Dirac was right. They were wrong. So you see, disregarding elderly, what happens with elderly people is they realize they can't keep up with youngsters by running. You can't keep running the same rate until you're 48, 50 as a youngster. But you may have wisdom. You may have instinct. You may be able to, and you say to yourself, well, if I get to contribute now, it's not going to be some trivial calculation. Anybody can do that, youngsters. I got to contribute something great. So you raise your stakes, you aim high, and then you tell people, I'm thinking about how you solve the problem of the universe. They say, oh, you're crazy. But sometimes they're right. And so that's the way old people make big advances. And the Chinese like the old people. There's one thing, if you go to China, and there was talk here before about China, the one thing I like about China, or the Orient, is they give respect to elderly people. America is a country for the young. China is a country for the old. That's why a lot of Chinese retire to China, because as you get older and older, you get more and more respect. So finally, you disappear into the clouds, and so yeah.
To end with, perhaps I could press you a bit on something you raised in your lecture about artificial intelligence.
Yes.
I remember many years ago, nobody thought that a computer would be able to play good chess, and now my smartphone can beat me at chess very easily. And now computers can check the proofs of theorems, so maybe they'll be able to find theorems. So do you think mathematicians will become redundant?
No, absolutely not, you see. For example, let's start with chess. Well, okay, computer can beat you at chess. But what invented chess itself? First, you see, we invented chess, and the computers just getting better at it. But we laid down the rules. They just copied us. Okay, that's chess. There are more advanced things now. Computers do much more complicated things. But the same sort of principle. They don't have the imagination to do something entirely new. They have the capacity to do what we do it much better. They have even the capacity to invent new rules. Because there are computers now who will invent new rules. But they will invent rather dull rules. They won't have the really imaginative ones that go way beyond. They won't be like Einstein or Shakespeare. They will not be like that, because that requires a creative human mind. And I don't think the artificial intelligence community has got anywhere near that. They delude themselves. They're the ones who do themselves. They're youngsters still. So I think, and I know that there's a very brilliant man I know, called Demis Hassabis, who runs DeepMind. This is the system which came supported by Google, and which not only beats people at chess, but beats people at Go, which is a much more difficult game. And they're aiming. I know the chap, he's a very brilliant man, and he said to me what he's trying to do is to develop machines that can have emotions. If you've got a machine that has an emotion, in principle it should be able to tell you whether this is a good, beautiful theorem or not. But I think even that misses the point, because we don't understand our own emotions well enough to create a machine that will do something similar. So I think I'm a firm believer in the human mind will always be ahead of anything else that's created by machinery.
Well, that's an optimistic note to end with. Thank you very much. It's been great fun talking to you.
Okay, thank you. Thank you. That was a big hand. Thank you.